In Newtonian physics, conserved quantities like linear momentum, angular momentum, and energy are neither created nor destroyed. They only transfer from one place or one body to another. Conserved quantities are useful, but their values vary by point of view. Consider two moving bodies. In the initial reference frame, kinetic energy equals 1.5 joules. In the frame of body A, energy equals 4 joules. In the frame of body B, energy equals 2 joules. Remember, even though the values vary, momentum and energy are conserved in all frames. Angular momentum varies both by frame of reference and by observation point. Remember, even though the values vary, angular momentum is conserved at all observation points. Tips for viewing. To absorb the full meaning, viewers should know how to slow, pause, and repeat. In YouTube on Chrome or Edge, the question mark displays all keyboard shortcuts. Some useful keys are shown here. The vector cross product. This limited explanation only covers aspects of the cross product relevant to angular momentum. For a full explanation, consult other sources. The cross product multiplies two vectors and produces a vector result. We will discuss A cross B equals C. The value of A is its length and direction. We can place vector A at any position without affecting its value. We can place the tail of B at the tail of A to see the angle between them, and label the angle theta. Arranging them to touch causes them to lie within a single plane defined by their two heads and their common tail. Length of C equals length of A times length of B sine theta. Units of C equals units of A times units of B. Vector C will always be perpendicular to both A and B. These background axes express distance units like meters or feet. Vectors with non-distance units, like meters per second, have no natural scaling against these axes. We simply choose any convenient scaling and draw our non-distance vectors. We then see the direction of each vector, but we cannot directly compare the lengths of vectors with differing units. Are meters larger or smaller than meters per second? They are incomparable. We can separate B into two components, a component perpendicular to A and a component parallel to A. We can ignore the parallel component. It contributes nothing to the cross product. The length of the perpendicular of B equals B sine theta. If we cross A with the perpendicular of B, we get the same value for C as before. A cross B will always equal A cross perpendicular of B. All B vectors that have equal perpendiculars produce the same cross product value. This is why textbooks say we cannot divide vectors. Given A and C, many different B can satisfy A cross B equals C. Given A and C, we cannot determine which B generated C. But we can define a useful vector cross-divide operation. We will represent it with a double slash symbol. C cross-divide A produces the only purely perpendicular B that satisfies A cross B equals C. C cross-divide A provides one component of whatever B was originally cross-multiplied. We will find all of B by combining components. One particle. Suppose a particle is traveling at a constant velocity. We can choose a coordinate system such that the particle is traveling in the positive direction along the x-axis. Consider the instant when the particle reaches -1 meters. To find angular momentum, first choose an observation point. R is the displacement vector from the observation point to the particle. R equals the particle position vector minus the observation position vector. P is the linear momentum of the particle. The units of momentum are kilogram meters per second. Due to the non-distance units, P is drawn with arbitrary length scaling, pointing in the direction of travel. Angular momentum, designated L, is defined as R cross P. We could directly cross-multiply these two vectors, but it is useful to separate R into two components, a component parallel to P and a component perpendicular to P. The parallel component contributes nothing to the cross product. We can ignore it. Perpendicular to the linear momentum is the same as perpendicular to the projected path. Multiplying the perpendicular component by p provides the entire value of the angular momentum. The angular momentum vector L is always perpendicular to both vectors r and p. L's forward direction is determined by the right-hand rule. The angular momentum vector is shown at the observation point. It belongs to this observation point. When we choose a different observation point, we likely find a different angular momentum value. Again, the perpendicular to path component is what produces the value of angular momentum. Angular momentum values form a circular pattern around the projected particle path. The position of the particle along the path and the position of the observation point along the path affect only the inert parallel component. They do not affect the consequential perpendicular component. The pattern existed and exists all along the path to both distant infinities, unchanged and conserved over all time. Observation points closer to the path have proportionally less angular momentum. Observation points further from the path have proportionally more angular momentum. Observation points on the path have zero angular momentum. Every possible combination of perpendicular to momentum components exists somewhere in this field. A particle with more mass and less velocity but the same momentum produces the identical angular momentum field. Because their fields add, this unequal pair of particles traveling in opposite directions with the same total linear momentum whose center of mass is traveling parallel to the x-axis also produces the identical angular momentum field. Notice that the center line of the field is displaced from and parallel to the path of the center of mass. This spinning body with its own local angular momentum, but the same total linear momentum, also produces the identical angular momentum field. All systems with identical angular momentum fields have identical total linear momentum. If we take the value of angular momentum observed at any chosen point in the field and subtract that value from every value of the field, the result is the portion of the field due only to the total linear momentum centered around the chosen point. This can be useful if the chosen point is the center of mass. A single particle with more linear momentum will have proportionally more angular momentum. Remember, for a single particle, angular momentum varies spatially at a constant rate proportional to linear momentum. For a single particle, you may already guess how to calculate linear momentum from angular momentum. Soon we will calculate total linear momentum for a group of moving bodies from 3 observations of angular momentum. Center of mass. Given any group of particles with total mass m, the center of mass is a calculated position, a weighted average of particle positions. At time t in the frame of reference where center of mass is unmoving, angular momentum observed at the center of mass is this. In another frame where center of mass is moving, but instantaneously with the same origin, each particle gains extra velocity. Angular momentum around the current position of the center of mass is this. Expand terms. Simplify. Cancel. Remember, angular momentum observed at the position of the center of mass has the same value in all frames of reference. If angular momentum is conserved, this includes all paths of the center of mass in all frames of reference. This fact can help find angular momentum when changing frames. Linear equations. Given a group of n bodies with total mass m, each body presents 6 unknowns, scalar quantities that represent position and linear momentum. If we know the value of angular momentum at one observation point, this single observation point will provide 3 linear equations. 3 linear equations are not enough to solve for 6n unknown variables. But we can make use of any number of observation points, producing 3 linear equations at each observation point. We easily can gather more equations than unknowns. If these equations were linearly independent, they would conflict. Instead, the equations are linearly codependent, which prevents us from solving for individual positions and momentums. But all is not lost. Landau and Lifshitz. Total linear momentum is defined as the sum of individual momentums. Total angular momentum is defined as the sum of individual angular momentums. Using only these two definitions on page 20 in their 1960 textbook, Mechanics, Landau and Lifshitz proved the mathematical identity equation 9.4. Equation 9.4 is the essential Rosetta Stone to understanding the relationship between total linear momentum and angular momentum. Let's derive it. This is purely math, direct from definitions, independent of any experiment. Equation 9.4 expresses a mathematically proven relationship between vectors and cross products. In Newtonian mechanics, equation 9.4 is mathematically true for any group of particles at any time t in any inertial frame of reference, as long as O1 and O2 are unmoving in that frame and P1 through Pn are taken in reference to that same frame, with or without external forces present, regardless of whether angular or linear momentum is conserved. Remember, we can use linear momentum to calculate differences in angular momentum. And given total linear momentum and angular momentum at one position, we can calculate angular momentum at any and all positions. Note that angular momentum becomes more complicated in relativistic and quantum physics. Mechanics uses equation 9.4 to prove the widely known result. Angular momentum at any point equals angular momentum around the center of mass plus angular momentum of the center of mass. Actually, angular momentum of an imaginary center of mass particle with the total linear momentum. But equation 9.4 shows that the starting point does not need to be the center of mass. It can be any point. Angular momentum at each point O2 equals angular momentum at any chosen O1 plus angular momentum of an imaginary particle at O1 with total linear momentum. So that is true for the center of mass and also true for every other point in the universe. But not every point in the universe can have the angular momentum pattern centered around it. If we choose a point as O1 and apply total linear momentum to an imaginary particle there, this is the pattern of angular momentum centered around the imaginary particle. When we add the constant vector value of angular momentum at O1 to every pattern position, we get the same pattern as when we started at the center of mass. Every point has a centered pattern plus a constant value, which may shift the pattern sideways to its true position. If total linear momentum p is non-zero, then every possible combination of perpendicular to p angular momentum components exists somewhere, and somewhere those components exactly cancel the perpendicular to p components of the constant value, which forms the field center line. If the constant value contains a parallel to p angular momentum component, it will result along the field center line. Equation 9.4 also provides another well-known result. If overall linear momentum p is 0, then O1 minus O2 cross p is 0. The portion of the field that spatially varies due to linear momentum is 0. And angular momentum is equal to the constant value at all observation points. Let's go further past what is found in current textbooks. Displacement equations. We next look at calculating linear momentum from angular momentum. If we have L of O1 and L of O2, we subtract them, then vector cross divide. But this does not produce the entire linear momentum. It produces the component of linear momentum perpendicular to O1 minus O2. But that is progress. We define a new variable for the displacement from O1 to O2. Equation 9.4c is always true, regardless of any forces applied. We can get components of p by solving multiple linear equations, but it is easier if we choose observation points wisely. If we choose O2 to be O1 plus some distance in the x direction, the equation delivers the py and pz components of momentum, which are both perpendicular to the displacement. This is almost identical to using vector cross divide, except cross division multiplies by minus I, which returns the components to their usual signs and positions. By XYZ symmetry, you can get all components of p. Using 1 meter displacements, we can make individual equations for px, py, and pz. Let's use these equations to calculate linear momentum purely from angular observations in a randomized example. Bodies, observations. We successfully calculated linear momentum from observations of angular momentum. Remember, we can use linear momentum to calculate differences in angular momentum. We also can use differences in angular momentum to calculate linear momentum. A specific spatial pattern of angular momentum indicates a specific linear momentum, and conservation of a spatial pattern of angular momentum implies conservation of linear momentum. The Jacobian. Starting with equation 9.4, at time t, p is constant. L at the origin is also constant. We can express L as a function of x, y, and z. We can look at the x component of L alone. If we hold y constant and plot Lx as a function of z, we see that Lx of z is a straight line with a slope of py. All components of L are linear with respect to x, y, and z. Notice that adding a vertical constant value would produce the same result as shifting the function sideways. This provides the sideways shift that we see on the 3D plots. If you had angular momentum values at 2 points on this graph, rise over the run would provide py. Vector division can calculate slopes in multiple dimensions. We can find the Jacobian gradient. The Jacobian is a matrix of partial derivatives. The Jacobian of L is populated with components of total linear momentum. Remember, given any group of bodies at any time t, the spatial rates of change of angular momentum are constant across all x, y, and z, and are equal to the components of linear momentum. Adding a constant value to L can have the effect of moving values sideways across x, y, and z. The units of the partial derivatives are kilogram meters per second, which are the units of linear momentum. The relationship between linear and angular momentum is similar to the relationship between acceleration and velocity. We use differences in velocity to calculate acceleration. We use acceleration to calculate differences in velocity. We use linear momentum to calculate differences in angular momentum. We use differences in angular momentum to calculate linear momentum. But the differences are taken across the 3 dimensions of space instead of the single dimension of time. Remember, at time t, total linear momentum acts as the cross derivative of angular momentum. Central force. Given a body orbiting the origin in a central force F, observed from the origin, angular momentum is constant. Over time, torque can transfer angular momentum to or from a body. R is the vector from the observation point to the body. Torque is R cross F. Observed from the origin, R is always antiparallel to F. So R cross F equals 0, torque is 0, and angular momentum is unchanging. This situation is often described as conserving angular momentum, but the conservation law demands that angular momentum is conserved at all observation points. Angular momentum is not conserved. 0, 0, 0 is just a point where the changes cancel out. Still, at any time t, differences in angular momentum give us all components of linear momentum. Linear momentum is expressed in the pattern of angular momentum across x, y, and z. Although one linear momentum value is associated with an infinite number of angular momentum patterns, each pattern of angular momentum expresses one exact value of linear momentum. the same particle in a different frame of reference where the center of force is moving, there is no observation point at which angular momentum is unchanging. Let's look at a system that conserves angular momentum, given three bodies orbiting in a moving central force in the y equals 0 plane. Linear and angular momentum are shown at the center of mass. The pattern of angular momentum is offset from the path of the center of mass. The pattern extends to infinity, conserved over all time. In this example, angular momentum has no component parallel to linear momentum. In every system, the rates of change of Lx, Ly, and Lz across x, y, and z establish Px, Py, and Pz. Remember, the entire pattern of angular momentum is conserved, therefore linear momentum is also conserved. Conclusions. Total linear momentum determines how total angular momentum varies across x, y, and z. Total linear momentum acts as the cross derivative of total angular momentum. Total linear momentum can be calculated from three non-collinear observations of total angular momentum. If total angular momentum is conserved across x, y, and z, total linear momentum is also conserved. Conservation of total angular momentum across x, y, and z requires and depends upon conservation of total linear momentum. Newton's third law provides the functioning of conservation of linear momentum. The strong form of Newton's third law provides both conservation of linear momentum and conservation of angular momentum.